All right, so we're running just a couple minutes behind here, but I'd like to introduce you to Ross Gibb and Veronica Valeros, who'll be talking about Adware's new upsell, Malware.
Thanks, Steve. Welcome, everyone. Thanks for coming. It feels to me like we're in the home stretch, which feels good. One thing about these kind of things is when it runs as smoothly, it's because a lot of volunteers and hard work leading up. So thanks to everyone that for their contributions. Okay, we're going to tell you a bit of a kind of a story about a piece of malware we discovered, as well as how it kind of fits into an ecosystem of existing adware and malware. It's about changing DNS settings on infected machines. We had a classification issue at the beginning, and once we had it classified and we had its capabilities, we kind of investigated its infrastructure and what it was actually trying to do as far as monetization goes. And we'll kind of wrap up some thoughts at the end. Just to introduce myself briefly, I work on the research and efficacy team at Cisco. It's for Cisco's, some of their endpoint products. If you're at the last talk, the products that Dave is talking about is one of those. Veronica and I actually work on the team that looks into it when the product falls down. So we're kind of aware that the product doesn't catch everything, so we do the legwork after the fact to improve it and see where we miss things. I love Clojure. There's unfortunately no Clojure in this talk, but if anyone's doing anything interesting with Clojure, I'd love to talk about it. And CTFs when I have time. So actually, Veronica is going to get us started. So it's my pleasure to introduce Veronica Valeros. She is at the Prague Cisco office, and she'll start us.
Okay, thank you. Right. Okay, so it's really nice to be here. I come from Prague, Czech Republic, so I'm still adjusting my brain to the time zone. I am a malware researcher. I work for Cisco Cognitive Threat Analytics. Basically, my day-to-day is analyzing network traffic from the behavioral point of view. Like I just look at proxy logs mostly all day and try to point which things are malware and which no. I have some background in machine learning, and I love Python, word driving, lockpicking, and I am a StarCraft player. So yeah. Okay. So let's talk about DNS Changer and how we discover it. And I'm going to talk briefly about what our product does, because that's our product discovered DNS Changer. So Cognitive Threat Analytics is a kind of a layered machine learning cloud-based solution for threat detection, and that sounds pretty nice. But in reality, this is what we do. Basically, we work on the after phase of the attacks. That means that our input, or the input of our system, is web requests, HTTP, HTTPS, and it means that if we see the traffic, you are already breached. Everything you have in place already failed. That's why I'm seeing the traffic of the botnets or the malware, right? So it's quite fun. And every layer of machine learning, what it does is to discard tons of traffic that is normal, because we get more than 10 billion requests per day, and that's not humanly possible to look at. Even if I try to do that, it's not possible. So our product, what it does is just every layer discards everything that looks normal, and looks for things that are malicious, and then it's just keeping the most malicious, more malicious. And what I actually do is I'm on the end of all the chain, and I'm kind of evaluating the stuff and saying, okay, this works or not. And so in last December, we developed and deployed a new classifier. It's called multi-instant learning classifier. I'm not going to talk about it. The research was led by one colleague of mine, Karel Bartosz, and he wrote a blog about that. You can check the basic concepts behind that. And so what I did is like, okay, it's been running for some weeks. Let's take a look at it and let's see what it does. So analyzing one domain at a time is kind of impossible, mostly if you're looking at a lot of traffic. So I focused on behaviors. So I just took all the stuff that this new classifier was discovering, that's the orange stuff. And then I grouped the rest of the behavior in like coherent groups. Like, okay, all the yellow stuff, I don't know what it is, but it looks the same. So I just put it in a category of unknown. Then I pick another group of behavior, and then I look one behavior at a time. Then, so that's what I did. And the first behavior, the yellow one, looks like this. Hopefully you can see that. So it was a long string of long URL. It was interesting because it has like 3 parameters. 2 of them were sending encoded data, which initially might seem like base64, but it wasn't. And it wasn't only that suspicious, but the same communication was going to several different domains, to some IPs that were kind of, okay, not very trusted. So it was enough to keep looking into it and say like, okay, what is this? That doesn't look like normal. So my process of analyzing, I cannot spend days or weeks analyzing stuff because there is too much. So what I do is like a first fast categorization of the thread. So I got network traffic, and then I get domains, IPs, or whatever ISC that I can get. Then I try to get hashes, and then try to get signatures. And signatures, if they are there, it means that antivirus vendors already see this thread, and then they just put a name on it, and luckily it's going to be correct. So from signatures, what you can get is like potential threats. Potential threats allow us to confirm the behavior or expand it, or at least have an idea of the risk of this, what we are seeing on the network. So after doing that, this is what we got. And this is usually a very nice picture when you are trying to categorize a threat coming from the network, because antivirus vendors never, ever, ever get a single signature for something. It's like you always, all the time, has to work with 10 or 20 different signatures, and you don't know what it is. So it's a problem because I cannot spend much time on it, and I really want to know what it is, but I cannot use this knowledge like this. So I don't know which threat it is, but at least I know some of these from my experience, so I can kind of cross over. And that usually works most of the time. So I know it's not Optimize or Pro, I know it's not Multiplug, I know it's, I don't know, Mickey, I don't know what it is. So after doing this, we kept some signatures and say like, okay, what is there something written about this that we can kind of have some lead? And there was some nice blog on December, just 1 month after we started looking at this, 1 month before, and they explained about Trojan Dynamo, and that was having some DNS Changer functionalities. So far so good. We say, okay, this looks like DNS Changer, some signatures kind of match the behavior. But then we started tracking this, and this is what we saw. This is kind of the amount of users. And between December and January, we saw a huge spike. Then we started worrying because our system generates alerts, and you don't want to generate alerts that are not accurate. Also, we need to put a risk on the detection, and I cannot say to the customers, yeah, this is super malware and it's Adware, right? And we have some Adware signatures like POA, so we were wondering like, okay, is this real malware or is something else? And that's the point where we decided to kind of look more on it, and Ross is going to explain how he did that.
Right. So what came to my desk was basically some suspected binaries and the URL patterns that the CTA product was detecting. So what I'm going to do for this part is just to take you kind of through a workflow of how I work through this. So, and it's going to demonstrate the use of sandbox and kind of where sandbox can let you down in some ways and where to pick up when it does. So what we're looking at here is a portion of a sandbox report. On the left here, you can see registry keys. This is a process that changed it, and this is what changed. So when I looked at the sandbox report, the first thing that stuck out to me is that a process called 2.exe was changing the name server of the system. So this is the location, the registry, where the name server is saved. So right away, it was very suspicious. Okay, so now we're looking at the process. So this is the processes that executed at runtime. So I found 2.exe is the one I'm looking for. A couple things right away to notice is the parent. So its parent process ID is 1992, which is the process just immediately above. The process immediately above, its name came from an automation service. So we have a lot of automation services that submit samples. So that name is not necessarily attacker chosen, but the 2.exe actually is. And here's where the file existed on disk when it was executed, and its command line arguments. So what I really want is the 2.exe binary. So that, again, this is just the disk location where it was, and this is just showing us that it was the same process that who's executed it also created it on disk. So knowing this, there's kind of like two big ways that 2.exe got on the system. It was either contained within the original sample that was submitted, or it was downloaded by the original sample. And we can see also from the sandbox report that there was network traffic on the system when the sample executed, and this is in the order in which the network traffic happened. So where the sandbox kind of fell over a little bit is that 2.exe was deleted at some point. And at the end of a sandbox run, we look on the disk for changes. So files that still exist on disk are usually easy to pick up. Ones that were deleted, we have a forensics module that tries to recover them. And in this case, it wasn't available. So it doesn't always work. But we have the original executable, and we have the PCAP. So we have a really good, we're going to be able to get to 2.exe. It's just going to take a little bit of work. So we have the original submitted sample, and it's a Windows PE executable. And usually the first thing you want to do is take a look at the PE header and structures and look for anomalies. That's like a typical like first step analysis. What we're looking at here in the top image is the sections of the PE. The names look really normal. The only thing abnormal here is the resources. The resources is enormous. This column right here is telling us the physical size on disk. So right away we know that this binary has resources. And resources depends on the binary, but it can be stuff like icons, images that the executable needs at runtime. So in this case, I can jump right to the resource section in the PE, and we can see some familiar strings. So anyone who's a Python developer will probably recognize Python 27.dll. It's part of the basic Python install. And then Python script is the second resource name. So I'd actually seen this before. This is a binary that's output by py2.exe, if anyone's ever wanted to create a Windows program executable from a binary, from a Python application that they had. And you can actually see, if you're familiar with what PE files look like in hex, there's actually the Python 27 here actually follows immediately. So what we have here is a Windows executable that has Python, like regular Python DLL, in the resource, along with a Python script, and at runtime it loads the DLL, feeds a Python script in, and executes. So it's actually pretty straightforward to get the Python script back. This is what it looked like, and we see sort of classic malware obfuscation. So I've cut a lot of this. This data string was enormous. There's a really short key. There's some basic base64 decoding, a very basic for loop, some more base64, some decompression. So a very simple deobfuscation loop. And then it uses the Marshall libraries, which are a part of Python. And these libraries they're similar to Shelve and Pickle. They actually they're used for serializing and passing around the actual Python bytecode. They're seldom used, but in this case, it's a nice way to load your malware sort of dynamically. The Marshall objects it's really easy to dump out the PYCs that make up the Python application. So we dump those to disk. And I'm not showing all the files. There's actually 75 of these, so it's a full-blown Python application. So now we've gone from a single PE executable to a 75-file Python application, which is not really a lot of fun because we're facing the prospect of sifting through all these files, and they're in Python bytecode form. So first thing we want to do is get them out of Python bytecode form, and I hadn't done this, I think, since I was a student. So I went looking on the internet for a decompiler. The reason I have this open, Jack Daniel talked about kind of standing on the shoulders of giants. John Aycock is on the faculty of the University of Calgary and was a professor of mine. So this tool is not his, but it was based on some of his graduate work. So when I see that, I'm like, oh, I'm in good hands. Unfortunately, I couldn't actually get this thing to work for some stupid dependency. So I just went to the easy Python decompiler. But thankfully, we're still based on that tool I couldn't get to work. We're still based on that, so I'm still standing on John's shoulders. So this is super easy. This takes in a directory and takes the PYC files and spits out Python. So now we have 75 Python actual source files, and there was no obfuscation of the programmer-defined symbols. So the symbol names you see here in one of the files, these are what the programmer defined them as. Okay, so we are looking for the 2.exe still, the 75 files, now that you have the Python source, you want to start looking for high entropy data or domains or network communication code. And it actually fell out pretty quickly, because if you notice the first network request from the sandbox report, if you just grep for this in the Python source, it brought you to this list here. So if you're familiar with Python, this is defining a list. So now you can see, okay, well, they're probably using this domain in some manner, and you have a Python variable. Now it's just a matter of going backwards through the Python code to see where it's used, how is the request generated, how is the response decoded, and move on from there. So there's actually 2 layers of that. So I just wanted to quickly just kind of go over the whole process. So the original samples here, the malware actually turned out to be something known called Mamba. It's probably named from this variable right here. And so the first HTTP post to neutralsky.info brought us back a second Python application, actually, an entire, probably 75 file Python application that was different from the first one. So that was stage 2. Stage 2 was then executed. Stage 2 then made an HTTP GET request to the next domain in the sandbox network logs, and that actually finally downloaded the 2.exe executable, wrote it to disk, and executed it. So this it's a little bit small, but this is the second stage. I'm just showing you that there was another entire Python application to go through. Okay, so we succeeded in getting to 2.exe. So what did it turn out to be? That was the code that was actually responsible for the DNS changing. So it was entirely in that binary. It was C++, so the analysis got quite a bit different after that. It maintains the CNC communication to update itself and report information about the system that it's installed in. And it also contains backdoor functionality. So if it gets a certain command, it'll actually open up a port and listen and execute commands. It has a file, it's in quotation marks, a fileless persistence method I'm going to show you on the next slide. And the URL obfuscation. So the URL that Veronica showed at the beginning, was built by this binary. So now we have that too. So we've got what the product detected originally. We found that executable, and we found who's changing the DNS settings. So to discuss the fileless nature of the malware. This is a way to do fileless persistence. So what we're looking at here is a typical Windows scheduled task that gets created. And in the run, rather than calling an exe that it's either written to disk or some kind of script, it's actually using PowerShell. So Dave's talk before this kind of talked about this. It's using the encoded command. So it's actually just passing a PowerShell script on the command line through a scheduled task. So the way that this persists is 2.exe changes the DNS settings, but doesn't save itself anywhere on disk. So when the machine gets rebooted, 2.exe doesn't execute anymore. However, it also, prior to it being deleted, it created itself a scheduled task with a PowerShell script, and the PowerShell script just starts up, reaches out to command and control to download basically updated copies of 2.exe. So that's its persistence mechanism. I call it sort of fileless malware because it's not writing a script file or an executable file to disk, but it is writing a scheduled task, which if you know how those are created in Windows, it's actually a file. So that's in contrast with some other fileless malware. So this is a different sample, but I wanted to show this to contrast. In a run key to run, you can actually specify JavaScript rather than a file on disk. So in this case, this malware is creating the run key in the normal place in current version run, but it's using a JavaScript file. You can see the W script here. So Windows actually, when it boots, it'll read this and execute it. I feel like this is a little bit more effective method because you are changing a file and that the registry hives are obviously on disk, but they already exist, so you're not. It's not something net new on the system. So I feel like this is a bit better fileless mechanism. Okay, and then back to the obfuscated URL parameters. So how we got started in the CTA data that Veronica mentioned. These were encoded. It looks like base64, and it's a variant of base64. It's just typical. They messed and customized the base64 encoding in the C++ binary. So there's not a lot of glamour in reversing this. It's just sort of like slogging through a bunch of assembly. And then once I did that and had a Python script that was usable, we could decode the encoded parameters. Because we're really interested in what we can tell a customer is what's being exfiltrated or potentially being exfiltrated. So what we're actually seeing is just system information. So this is a hardware ID generated uniquely for the infected system, an OS ID for what version of OS and stuff. So it's checking in with its command and control, telling it what it's infected. So we didn't see any usernames and passwords. Okay, so we needed to classify this. We knew even from the sandbox that it was changing the DNS settings, so it was bad at the beginning. And for these reasons and more, it's malware. So it installed with no user interaction, all that obfuscation layers and whatnot. That's all typical of malware. Shady domains, and I didn't show this, but it also installs a root certificate so that it can actually do its monetization, which I'm going to show you. Okay, so why did it go to all this trouble? Why did it change your DNS settings? So it's advertising, naturally, right? How do you make money on the internet? You advertise. So once your DNS settings are changed to the malicious DNS server, most of your DNS requests that go to that server are served back to you correctly. So when you go to look up google.com, you actually get an IP address of google.com. But there's a subset of domains, most of them owned by Google Advertising, the portion of Google that deals with advertising, where it does want to alter them. So in those cases, the request goes to your malicious name server. One of the examples is Google Analytics. So when you ask for Google Analytics, you get an IP address that is not Google Analytics. It's also attacker controlled. So next you send a GET request to Google Analytics. What you think is Google Analytics, it's intercepted by the malicious Google Analytics server, who actually proxies your request to the real one because they want to return you the real Google Analytics data. It's just they inject some JavaScript on the way back. So they have a list of domains they target, and they have a list of resources that they know that they can inject into, and they're basically trying to replace advertisements that Google's trying to serve to you with their own. So we can take a quick look. This is actually what they're trying to inject. So when it goes out to Google Analytics, the response comes back to the malicious server. Before they send it to you, they inject this, which is like a very simple bit of JavaScript that is just basically loading another piece of JavaScript from another server. So that JavaScript, and we're not going to go much deeper into this. Where we want to stop is what looks like affiliates are all at the domain called dnsunlocker.com. So then it's like, well, let's check out what's going on in dnsunlocker.com. So this is what the website looks like. If you're playing at home, just don't go here because it's an adware, and it's sort of marketed itself as an adware. And you can see that there's uninstall instructions. They've got like graphics and images. It kind of looks somewhat legitimate, but it's doing the same thing as the malware we just looked at. So now we had a case where we went back to the sample store and we could find all these samples that were installing a version of Adware that was doing the exact same thing, changing your DNS setting, using the same DNS infrastructure, the same malicious DNS servers as the malware we were looking at. But this one was Adware in that it had uninstall instructions. If the Adware version got installed, you had actually an uninstaller. So now we have, basically what we're sort of observing is an adware that has two kind of business models, an adware side and then a malware side, where in one case it hides and in the other case it doesn't. So just to compare those two, so the version you get from dnsunlocker.com, you can't actually download anything from there. It gets, the dnsunlocker.com version gets installed when you, through other software bundles and whatnot. So, but they provide you with a nice license.rtf, which says somehow you've agreed to have this software on your machine. So with the malware we looked at, we didn't see any of that. There was the only thing written to disk at the end of the day was that scheduled task and then the certificate that was installed. They both do no-ask installs. In the case of the Adware version, it usually is bundled with something. DNS Changer was just getting installed as like maybe an attachment. They both did DNS hijacking. They both installed a root certificate so that when you were going to an HTTPS protected website, you wouldn't get any certificate warnings. So the DNS Unlocker, though, did two different things. It provided an uninstaller, which on the versions I attempted, it actually worked. And it also, it didn't do any kind of hidden installation. So the binaries that came with the dnsunlocker.com version, they were just in program files. Whereas the DNS Changer, like I was showing you, just had the scheduled task. So a much different means and attempt to hide from the user. So I'm going to pass it back to Veronica, who is going to take us through the infrastructure.
Okay, so once we mapped all this activity, the next step was like, okay, let's analyze what these guys pull out and let's take a look at it. So we enumerated all the servers they had, and then we started classifying them by type of functionalities. So we could divide them in 3 functional groups, and the first one is like the command and control servers. All the 3 groups do not overlap each other. They are like quite separated, so the command and control servers only act as command and control servers and so on. So the command and control servers were only 3 of them, which is quite small, I would say. The main purpose were to basically control the bot, provides domains, new domains to contact, updates to the bot, and also collect all the information that the DNS Changer was sending outside, like all these statistics about operating systems and others. And all the servers were located in Netherlands, and the bot was, DNS Changer was not contacting directly the IPs, so these IPs were hidden behind some domains infrastructure, and we collected something like 136 domains that the bot was communicating with. All of them registered through some privacy register, so we didn't have much information from them. And then we have the DNS name servers. That's when the bot executes on the system. It will replace your normal name servers for a pool of these ones. And there were from 5 to 8 of these servers. And the purpose of these name servers is just to choose which sites to intercept and which sites to let go. So if you're looking for, your machine is asking for well.com, they will respond with the normal IP. If you're asking for Yahoo, they will do the same. If you ask for Well Analytics, they will respond with the malicious IP, right? And these servers are located in 2 different countries. Some servers are located in Netherlands and others are located in Israel. And we kind of wanted to target the target sites. I mean, they are modifying or intercepting Google Analytics and what else. So it's quite hard to do because we had to do some kind of manual queries to the name servers to see what they were responding or not. And we found at least 9 target sites, and most of them, almost 7 to 8, were all Google services like Google Analytics, Google Tag Manager, another type of advertising. Probably because if the DNS Changer advertising activity is not so huge, probably Google will not notice. It's just a couple of hundreds of users doing this, right? And then we have another different group of servers. Those are the injection servers, and the functionality is to actually provide the injected resource. So when the infected host asks for Google Analytics, they will respond with a malicious IP, and that malicious IP is picked from this pool of injection servers. And they were also around 7 of these servers. And we also tried to kind of enumerate how many unique resources they were injecting back to the users. And we only found 4 of them. And all of them were very similar to each other, and mostly all of them related to advertising. But that doesn't mean that this is not going to change. Once they have all this infrastructure, they can inject every JavaScript that they want, right? And all of these servers were also located in Israel. So we wanted also to look at the domains, because it tells a lot about the intention of the attacker when you look at the infrastructure and how it was set up over time. If it's somebody that really thought this through, sometimes this activity is spread over years or at least months. This was very, very fast. So the first domains that we saw were registered in September. And the first activity we start seeing about DNS Changer, looking back, was late November, which is not so long after the domains were registered. And so the main activity, registration activity of the domains were in December. And after January, there were no more domains being registered. And we don't know that this is because they just got all the infrastructure they wanted, or maybe they started getting attention, or something else. And the yellow point is where we saw the spike on the infected users. So we took all the 3 different CNC servers, and we tried to see the activity and how many domains were related to each other, to each of them. And during the first month of activity, it was just 1 IP. And then they started getting more users, we guess. And then they switched to two new servers. But there is just one that is kind of getting all the heavy load. And it's not that huge of a malware, let's say. It's quite small compared to other botnets, but it's quite interesting that they can manage all these users with just 1 IP. And 1 IP was kind of inactive for some time. So another thing we did and was interesting is that Ross told us that how he break the encoding of the URL. So we took like 4 months of traffic, and then we decoded all the URLs and said like, okay, well, what is going on? What the DNS Changer is sending out? Is there something interesting in there? And well, there are a lot of parameters that the bot is sending out that we cannot share because it was some information from the users. But what's interesting that for a kind of likely wanted to be Adware, they were doing some checks for analysis tools on the system, not only checking the existence of these tools, but also sending the information out to the command and controls, right? And they were checking for VMware components, many of them. They were also checking for VirtualBox, Fiddler, and also for Wireshark. That was quite surprising. And then we wanted to see how the operating system of the infections were, like the distribution, how it was. And so Windows 7 seems to be the most infected platform, along with Windows 10. And that's good news. It's not XP anymore. So we are good, right? We are evolving. So then we started trying to say, okay, we know this, what this does, how the users are actually getting infected, right? Because it's something that we can. Is there something we can do to stop this? It's like, I don't know, ransomware is being spread through phishing or spam emails. Okay, what is the delivery method of DNS Change? And in most of the cases that we observe, almost all the cases, it was through software bundles. Most of the common adware was not, if you Google for any of these, it's plenty of write-ups in the internet. So system healers, one system care, Adware multiplug, Optimizer Pro, and tons of ad injectors, different families. The one interesting thing about this is that most of these adwares are in the systems for months, or I don't want to say years, but really for months. People should develop some kind of tolerance for adware, that you get infected with adware, then you will start seeing most likely pop-ups with advertising, then you are shrinking your screen to work in this where the advertising is not there, and you are not remediating that. Nobody is. So it's like the adware is there and it's piling over, and you have tons of it in the same machine, and nobody cares about that. And suddenly we have a case where customers were starting worrying about this because, okay, this adware can actually deliver some malware, and I don't want malware. I know malware is bad, but I didn't know adware was bad, right? So in the end, antivirus vendor categorizations, they are doing a good job detecting, but it shouldn't be like the final truth. You should kind of assess the real risk every time you get a threat by yourself. Like, okay, you just need to gather all the information available and take your own decision. Also, adware are still infections. We want to have users that are not infected, at least for a month. Like, can you keep it like this? And it's very difficult. And for us, like every infection, or even if it's teeny, it's like an open door, right? And you don't want to have that in your system. And so the best way is like to kill the threat escalation chain in the beginning, like remediate whatever it is, remediate your system like ASAP. And then most of the time, incident response teams just remediate and then move on, and then the next month they come again to the same computer, they remediate again, and they go on. And educating users is really hard, but I think they are the ones clicking on the software bundles. They are the ones accepting the licenses. So they are the ones that should help us prevent all these massive infections. And then yeah, malicious actors will always seek getting revenue and more revenue, and they will use whatever means they can, right? Even if it's adware installing your system, and they will pay for getting access to your system. So be prepared. And lastly, this is not the first time we see this type of threat. So Ross is going to tell briefly about this.
Yeah, so this part's just a bit of an afterword. So once I came up for air after sort of finishing the analysis and writing the report, it felt like I'd heard this story before. And if anyone remembers, there was an old DNS changer. It was in 2007. It was operated by a similar kind of setup where it was a quasi-legitimate Estonian company, and it did the same thing. It changed your DNS settings. They were doing a drive-by download kind of install. And what I really remembered was the FBI operation. I'd forgotten that the name was Operation Ghost Click, which sounds really impressive. And that was the one where the FBI raided the servers overseas, the DNS servers, and then actually operated them for about 8 or 9 months, so that people infected with DNS Changer at that time would not lose internet connectivity. And they also worked with some ISPs to also continue the DNS after the FBI actually stopped running the servers. The part of the story that I'd forgotten, and there's a working group. There's like a working group about this. Their website is still up. All the material's still there. There was a number of indictments in Estonia. It took the wheels of justice moved slowly. They were eventually extradited, actually, to the United States. And one of them pled guilty. I'm not sure the status of the other cases, but he was actually just sentenced to 7 years in federal American prison in a court in New York on Tuesday, like 3 days ago. So this whole thing is sort of coming back around in a bit of a circle. So then I started thinking about, well, there's an old one that had a specially named FBI operation, and a new one that is admittedly smaller, but if I was the person running the new one, I would be worried about 7 years in U.S. federal prison. There's a couple differences though. They're both altering DNS settings and root certificates, and they're both monetization schemes. Is advertising. They were doing the same kind of thing, which was just changing web requests, putting in their own advertising, and getting paid for those advertisements. What the old DNS Changer did, it did two things wrong, in my opinion. One is that it was extremely aggressive at spreading. It was setting up, it would advertise as fake DHCP on the network in order to advertise the poison DNS settings to attempt to get other systems to use the DNS settings. And probably the final nail in the coffin was it was redirecting like American government websites, like irs.gov. It was sending irs.gov to like a tax preparation service. So maybe the new author sort of learned how to stay enough under the radar that the U.S. federal government won't come knocking. So thanks for everyone's attention. That's it. And we'll take any questions if there are any.
Over here.
Hi. Go ahead.
If an infected machine had an AdBlocker, would the ads still be served?
So the AdBlocker will only avoid you to see the. Oh, thank you. You will not see the advertisements being injected, but you are still infected, right? So I think that in that case it's kind of negative because at least you're not going to notice that you're infected and you cannot remediate.